Hey folks, so this is a discussion on section 10.3. It's an introduction to vectors. You'll notice that I've drawn a vector over here on the right side of the screen. It looks a lot like the ray that we used to have in geometry, but it does act differently than that. We'll discuss that. First, let's talk about the parts of a vector. You'll notice that every vector is going to have an initial point. This is the starting point of my vector. And then a vector will also have an ending point or a terminal point. So as we look at the picture of a vector, this guy right here is going to be the starting point or the initial point, and this guy right here is the ending point or the terminal point. And you might say, well, an arrow means that we go on forever and ever and ever, and that is not what's indicated here on a vector. A better way to draw a vector would be just to draw a normal segment that has an arrow somewhere in the middle. This shows that I have definitely a starting point, I have an ending point, and that this arrow tells me what direction my vector is going. We're not going to draw our vectors like this because that's not the common universal way to do that, but please understand that this arrow does not say it goes on forever. This arrow tells me which direction my vector is going. Then we also have something called a scalar. A scalar is simply a number that we typically use to multiply. If you'll go down the page a little bit, this -3 is a scalar because I'm multiplying it by my vector u. And so that's an example of a scalar. So then we have a special case scenario called the position vector. The position vector has the initial point or the starting point at the origin at 0, 0. The ending point is at some other coordinate on my graph. Now, I'm going to call this coordinate one of two things, and I will go back and forth, so get used to both of them. You could say it's at the coordinate AB, or you could say the ending is at the coordinate XY. I will be using both of those. There's two different ways to show that it's a position vector, this special case scenario. The first way is to put the coordinate, the AB or the XY, inside of pointy brackets. Those pointy brackets tell you this is a position vector that ends at that coordinate. The second way that you could show that it's a position vector is by using i's and j's. And so this is ai plus bj, or you could say xi plus yj, using those same a's and b's or x's and y's that I used for the coordinate. Now, if you'll go down a little bit in the notes, and we'll talk about magnitude and direction. And as you saw, my Apple Pencil is running low on battery, so this will probably be the last thing that I cover in this section. And magnitude, what exactly is magnitude? Magnitude is simply how long my vector is. So if I want to measure the length of my vector, this is going to be called the magnitude. The way that you write magnitude looks like absolute value symbols. So I would say that this is, the way I'd read this is the magnitude of vector v. How do I find the length of a vector? Well, if you think about it, if I have a vector drawn, and maybe I know the x piece and maybe I know the y piece of my vector, how would I find out how long it is? How would I find out this value right here? All I have to use is the Pythagorean theorem. That will tell me how long my vector is. Then we have the direction of a vector. The direction is going to be called theta, which is kind of nice because that's what the direction angle has always been called. And so when you look at the picture that we just drew, the angle at the origin is going to be called theta, exactly the way we did back in chapter 8. And then the way that you can find your theta, if it's already on the unit circle, you can use SOHCAHTOA. If it's a value that's not on the unit circle, well, think about what finds angles. We know that inverses find angles. We could use sine inverse, we could use cosine inverse, but since I know what the two legs are, the x and the y value, the a and the b value, then I could use the tangent inverse because the tangent inverse uses both x and y. Over on the side here, two vectors are going to be equal to each other only if their magnitudes are equal and their directions are equal, their thetas are equal. So you have to have both of those two things in order for two vectors to be equal to each other.